Hello, everyone. I have the pleasure to welcome you to the 7th episode of our webinar series on R&D activities on sCO2 in Europe that is conceived by ETN Global. For those that do not know us yet, ETN stands for Energy and Turbomachinery Network, and we are an international membership association representing the entire turbomachinery technology value chain. And my name is Jitka Špolcová, and I work as a project officer for ETN Global. In the past, you probably know that we had a few sessions on component challenges, and last time we concluded by the balance of plant. And today we have quite an exciting topic, quite different from the others, called sCO2 cycles for nuclear power production. And obviously know that because you have registered for this webinar. This webinar is, as always, conceived in collaboration with a few EU and national funded projects whose logos you can see on the screen. When you receive the presentation, you can click on these logos and learn more about these projects. As always, I need to tell you a few topics for a seamless webinar experience. So I have to inform you that this webinar is recorded. Your mic and cameras are off by default. But at the end, for the Q&A, you will be able to ask your questions and speak. If you have a question, we have a Q&A foreseen as a part of this webinar application. So you can ask your question via the Q&A. I hope that you will be able to see these Q&As because sometimes the technology tricks us. I have posted a test question, so if in case you can see it, then you will be able to see also the questions. In case it doesn't work, just use the chat. We will have a Slido question, so get your phone ready. And as I said already at the beginning, you will receive the presentation after the session, so you don't have to take many notes. And now, who are the people that are the most important people of today? So obviously the moderator and 3 presenters. So the moderator is Albannie Cagnac. The first presenter is Otakar Frýbort from Nuclear Research Institute Řež. The third one is Levisse from NAAREA. And the third one is Jack Akers from the UK's Atomic Energy Authority. I'm sure that Albannie needs not much of introduction, but anyway, as I will do for the rest, I'll also introduce her. So Albannie is an R&D project manager at EDF for already more than 16 years. She's currently focusing on technological perspective and innovative processes. She has been working on sCO2 since 2014 and has led 2 European projects dedicated to this technology. I'm sure that you have heard about these projects. They are sCO2 Flex and sCO2 for NPP. Well, but anyway, before I let Albannie speak, I have a Slido question for you. So take your phones and scan the QR code. And once you are done, the question is as follows. So what is the first word that comes to your mind when you are thinking about nuclear power generation? So try to make your answer in 1 or 2 words, and you can obviously also upvote other people's answers. We have already quite many answers, but there are still some people typing, so we can allow a little bit more time to let everyone finish. Well, Albannie, I think that you can already take the floor because, yeah, still there is still more coming, but I think that we already have a lot, so it will take a little bit of your time to debrief.
Okay, thank you, Ilka. So great. What I see is that for a lot of people, when we speak about nuclear, we speak about SMR. So one of the new design for the nuclear plant, but don't forget all the current generation of plant, because some studies, as we will see, could be done for this type of plant. And so, yes, I can't just say yes for the carbon-free energy and clean energy, because nuclear is, we will see it, one of the most carbon-free energy in the world, and also the safety, the waste, and also cost are also a part of our studies for all the nuclear reactors in the world. Okay, so I think it's okay now for this this crowd. So I will just share my screen.
I will stop sharing. That's a great introduction for your introduction.
It's a very great introduction, because we will speak about SMR, we will speak about safety, and we will speak also about fusion. So yes, it's a great introduction. Is it okay for you?
Yes, we can see your screen in the presentation more. Perfect. So, thank you.
I will just briefly make an introduction about nuclear, because as Jitka already said, nuclear is not really the core discussion of our webinar series until now. But why did we choose to speak about nuclear? It's just that nuclear energy is not really so different from the current coal and gas plant, because, okay, we use some nuclear power, we use fission, and one day nuclear fusion for produce electricity, the heat to change water in steam for the main plant, while the thermal power plant use heat from burning gas or coal, okay, to produce electricity. But both concepts need some turbine, some condenser, cooling system, heat exchanger. So today we will mainly speak about the use of supercritical CO2 for all the electricity production part of the nuclear plant. We won't speak a lot of what happened in the reactor, but a little, because it's quite important, and we will share why what happened in the reactor will help us to use supercritical CO2 for the secondary and the other loop of the plant. But it's really important. I just want to say that there is a lot of difference, but there is also a lot of common points. And you will see today in the discussion that some points that we already emphasized in the last webinars on the component are the same for the nuclear energy and the use of supercritical CO2 in the nuclear energy. What is currently the nuclear energy in the world is that nuclear is currently 10% of the worldwide production of electricity. So more than the solar, the wind, and the geothermal, and less than the hydro. And we still have the coal and the gas as first plant. But things are changing. And for example, in Europe, so in the European Union, we have now between 22 and 24% of the total electricity which is produced with nuclear energy. You can see that a lot of countries are already using nuclear energy in the European Union and also in the UK. And we will see in the next slide and with all the presentations that there is a lot of project in order to maybe have more country or more design with nuclear and supercritical CO2. But why do we choose nuclear technology today? Because I think that in the mind of a lot of people, and for example me some years ago, we see, okay, nuclear plants are the same since the 60s, so, but now we have a technology we involve with the scientific and engineering advance. So yes, we have the first generation in the 60s until the 80s, and now we are currently using the generation 4 with some concept like you already heard about VVER, EPR in Europe, but also APR, or for example the AP1000 with the Westinghouse. And we have to know, you have to know that since the first ideas of nuclear energy used for electricity, we also think about the generation 4, so all this innovative design, so with some gas-cooled fast reactor, some molten salt reactor, you will heard about it today. So currently we are using the generation 2, generation 3 also of nuclear power, so with mainly water and steam, so what we call the power pressurized water reactor. And we are studying, we are preparing and thinking about the generation 4, and we will present you today a lot of design which are currently from generation 4 and also one design from fusion. Why use supercritical CO2 in nuclear? You have to think that the first researches with the use of supercritical CO2 cycle in nuclear are from the 60s and the 70s. It's not a new idea. For us nuclear people, we think about the use of supercritical CO2 since a long time, because we already discussed in the former episode that we think that properties of supercritical dioxide carbon could be very interesting for us. High density, good temperature for us also. And as we already spoke about the properties of supercritical CO2, we have a lot of generation 4 concepts like the sodium cooled fast reactor or maybe a molten salt reactor, which are at good temperatures and good pressure for the use of supercritical CO2 for the secondary loop. So after the reactor in the nuclear reaction. Okay, so that's why since a long time we think about this idea. And if you are looking for some studies, there is a lot of publication in the 60s and until now which are dealing with supercritical CO2 and nuclear use. But why today do we choose to speak about this? Because it's not a really new subject. It's just that since some years, we have a reviving interest in the nuclear potential for the global transition. Why? Because as you say in the cloud, nuclear is a low emission energy, so carbon free, compare it to the coal, the gas and the oil. But also with the idea of this global transition, we will have a higher demand of electricity and energy in the world. And to be able to reply to this higher demand, we have to think about a lot of production, carbon-free production. So renewables like wind, solar, or hydro are a good solution, but we cannot melt all the figures. We cannot meet all the demand with only this this energy, just because okay, we will have solar, we will have hydro, we will have wind, we will have storage, but sometimes we will need to have a very reliable and safety flexible energy. And we think that we can see in the new scenario, so from EEA or European scenario, also in outside Europe, we will have a combination of this energy. So renewable, carbon-free energy, and nuclear. It's not a competition between all this energy, it's just combination. We need all this energy to face to the challenge of global transition. Also, what we see in the last year is that maybe the thing to use nuclear for non-electrical application. So with a nuclear reactor, as I say, we produce heat. So if we have the current transformation plant, we will produce electricity. But we can maybe put some other transformation plants and maybe have a use of this heat for the industry use. But also we have some design for district heating and nuclear energy, and also desalination. So if we want to use nuclear for the higher energy demand for this new application, what we can say in the different international scenario and projection for energy is that we will have an increased power capacity of nuclear in the next years. So as you can see, it's not only nuclear people who say that, it's EAEA, it's also some projection of GIAC report. And that's why since some years we see new R&D programs or construction in US, in France, in UK, all around in Europe. We think we have all this question about the new design. And that's why today we will speak of some of new design also, mainly because what are these new challenges for the competitiveness for this nuclear? We have all this new design, as you point in the crowd, which are the SMR. SMR is for small modular reactor, and also we have what we call the advanced modular reactor, which smaller reactor and maybe some new design. What is a small and what we expect for these SMRs is that the plant will be we need to be a fraction of the size of the conventional nuclear plant. So for that we will need compactness, and that's why we saw in the former episode that a cycle with supercritical CO2 could be very compact. We think also we need to have modularity, so to be able, for example, to have a factory assembled plant to transport it as a unit in the location for the installation. And we saw in the former episode that this modular question to have integrated units is also a question for the supercritical CO2. And also, so the reactor, not only to produce electricity, but to generate the heat and maybe heat at a higher temperatures at the current power plants that are around 300, 400, so to produce higher temperature heat. And the new concept of SMR can produce this energy. But there is a lot of challenges, and as you maybe see in the different papers, in scientific communication, all people who are looking for SMR are already working on all these challenges. So there is some technological innovation in order to maintain the efficiency, to increase the safety of this plant, but also the cost competitiveness of this plant is a great question for the people who are developing this. There is some question about the policy and the regulatory, because to develop new technology is very interesting, but for the nuclear people, we have a lot of qualification, we have a lot of standardization as all the other energy, and we need to have technological innovation will meet this regulation, and also, as you put, the safety and the weight management. And that's why we will see in the next presentation some concepts we are very interesting because they already include all these questions. And we think that with the advantages of the supercritical CO2 cycle that we already discussed in the previous episode, we can make a good choice of technology for this type of new reactor. Maybe not all the 6 new design of generation 4, but for 2 or 3, and also for the fusion. And that's why today we will present to you with all the different presentation. So I will just say thank you for attention, and we will go to the next presentation. So if I remember, it's Otakar Frýbort for Civil Řež in Republic in Czech Republic, who will present us what they are looking for and what they are studying currently with supercritical CO2 cycle and nuclear.
Thank you very much, Albannie, for the enlightening introduction. It was great to listen to you. And indeed, the next speaker is Otakar Frýbort, who graduated from the Czech Technical University in Prague in the Power Engineering department. Since 2012, he has been working in the Research Center Řež, currently as a head of Advanced Energy Technology department. He has more than 16 years of experience with R&D projects, and for the last 11 years, he has been focusing on the sCO2 technology. So, Otakar, the spotlight is on you. You are still muted.
Thank you. I'm sorry. Let's go once again.
Yes, yeah.
Okay,
yes.
now
yes, now it's perfect. Yeah, we can see it.
Okay, thank you for introduction, Jitka. And yeah, let's start. I will briefly introduce you the use of CO2 in current or on some previous nuclear reactors. Then in my presentation, I will show you very shortly some general comparison between Rankine and Ericsson-Brayton cycle. And then I will introduce some selected reactors which are currently under development worldwide, which uses CO2 as a power cycle. Then I will shortly touch some issues for implementation of CO2, but I'm afraid I will just repeat what Albannie just said. Then I will shortly talk about what we can do with some demonstration of CO2 cycle, and I will go to my conclusions. So, most of you who are familiar with some nuclear energy, you should know the AGR nuclear reactor, which was developed in UK and firstly commissioned in 1962. It's the nuclear reactor which is driven by thermal neutrons, so there is a graphite moderator, and the CO2 in this case is in gas phase, so it's not supercritical, it's subcritical, and it solves just for cooling of the active core of the reactor, and the power is generated through Rankine steam cycle. And in this case, this was not a first reactor, it's some kind of continuation of Magnox reactors, but some of AGR cells they're operated in UK. Then I selected another example, which is also quite similar. It's again controlled by thermal neutrons. It means that it's also moderated, but in this case, this was a design from Czechoslovakia, and it was commissioned in Jaslovské Bohunice in 1972. This reactor was moderated by heavy water, and again, CO2 was subcritical and used just as a coolant of the reactor core, and again, the power production was done through Rankine steam cycle. In this case, it finished with the pilot, as there were 2 accidents during 5 years of operation of this reactor, and just 100 grams of silica gel forgotten in the fresh fuel assembly caused partly the melting of the core and the accident, which totally stopped the operation of the reactor. Now, very shortly, why should we use CO2 in new reactors? So, as you know, probably even the Rankine cycle can be quite simple or quite complicated. It depends on the structure or architecture of the cycle layout, and the same or maybe more complicated cases with sCO2. As you can see there, it's possible to design simple Brayton cycle with regeneration, or some more complicated cycles like with some intercooling or reheating. There are some recompression cycles, precompressions, partial cooling cycles, and the final selection of the cycle depends on many boundary conditions and on the final goal of this application. So what can decide about the cycle architecture are the maximal temperatures of the cycle, or let's say the quality of the heat. Of course, also temperature drop, which is interesting. It's different case when you use it for coal power plant, and different case when you use it for some Gen 4 reactor. And of course, probably mainly the goal is some highest efficiency, but also there can be some cases where the cycle should be just reliable, and the efficiency is not so important. So it's quite tricky to select the best cycle configuration. And now general issue or general comparison with Ericsson-Brayton cycle. I use this picture, which is quite familiar. It's 20 years old, from Václav Dostal thesis, but the thermodynamics didn't change much since this time. So even this graph, it's quite current. So you can see the blue line. This shows the efficiency of current superheated steam cycles. With this technology, we can reach the efficiency up to 42% generally, or something like that. Then we can, of course, use supercritical steam cycles, which are also operated, and they have generally higher efficiencies, but there are, of course, some limits. The efficiency can reach something less than 50%. I could see some studies about 48% of the cycle. And now the advantage of CO2, generally the efficiency is higher in comparison with the previously mentioned cycles from approximately 550 degrees of Celsius. But there are, of course, other benefits. I didn't focus my presentation of the benefits of a CO2 cycle, as it was discussed many times, but like Albannie said, modularity, small dimensions can be advantage in comparison with supercritical cycles and so on. And now I selected 3 quite interesting projects which handle with sCO2 and it combines CO2 cycle with some of nuclear reactors. The first case is a design of TerraPower, where the CO2 is used as a primary coolant, and in the same way for production of the electricity, it means it's a direct cycle. Thermal power of this reactor is 500 megawatts, and what is interesting, the temperatures are 550 degrees Celsius with 22.5 megapascals, which can be quite challenging together, but in this case, the expansion is splitted, so in the nuclear reactor there is not a full pressure and full temperature, but some, I don't know the value now, but it's quite interesting design, and gross efficiency is calculated to 41% and overall efficiency to 36%. So you can see that that it's a benefit in comparison with current PVRs. And the next 2 examples are more, let's say, future reactors. As in this case, this design was designed by CVR, by my company, and in this case, the reactor core. Sorry, I forgot to mention in the previous case. This is designed as a fast reactor, so it's a very compact core. And in this case, it's a thermal neutron-driven again. The primary and secondary cycle is cooled by fly bee salt, and the tertiary cycle, the power cycle, it works with sCO2. Maximum temperature is set to 600 degrees with 25 megapascals of pressure, and the efficiency is calculated to 40%. And it's not that high, but it's affected also by the size of the cycle. So it's quite small, and the turbine, the power of the turbine, it's about 7 megawatt. And the last of the selected cases is from Korea, from KAIST. They call it micro-modular reactor. With where the CO2 is again in a direct cycle, so it's direct coolant of the core, and it drives a turbine with most challenging parameters of these 3 projects, where the temperature is set to 650 with 20 megapascals of pressure, and again it's quite small, like we can see it from its name, micromodular reactor, and the efficiency is due to it 33%. Now, about some issues which I can see in implementation. We can make a list of issues, but I selected, from my point of view, the most important ones. One issue is that for generation 4 nuclear reactors that are mainly the technologies, the reactors are cooled by liquid lead, molten salt, gas, and other concepts, and mainly instead of the supercritical water reactor, the reactor pressure, or the pressure of the media in the core, it's up to 70 bar, and even with some concepts, it's ambient pressure. So it's quite tricky to combine this low pressure primary cycle with secondary cycle with the pressure of 25 megapascals, which is quite high. But probably the key issue is the licensing of the reactors. It's quite challenging to license even 3+ generation, some PVR or BVR reactor. And now we are coming with completely new technology, which was not fully verified. and we don't have any data about reliability of the components and so on and so on. So the technology needs to be demonstrated at first to be used then for application with nuclear reactor. And from my point of view, the best applications where we can demonstrate the CO2 cycle and to find out its reliability and so on are, for example, the waste heat recovery systems or some thermal energy storage systems, or there are some projects for CSP application combined with the CO2 cycle. And what we can do, or generally what we do for that, so we build different experimental loops worldwide. The most famous, it's probably in US in Sandia, but there are also some smaller loops in CVR or in Europe, for example, in Wien on Technical University of Vienna. And currently, in US, again, there was commissioned, or it's being commissioned, the STEP project, which is 10 megawatt cycle, and the next 3 cycles, which are listed here, Sofia, and in frame of the Solar School project or desalination project, that are 3 prototypes which should be built with a megawatt scale turbine in Europe. So that's the way how we are going to verify and to obtain all necessary missing data. And my last slide, conclusion. So definitely using of CO2 cycle, it's the way how to improve the efficiency of nuclear reactors. I didn't mention it in my presentation, but it's probably useless to combine PVR or BVR with sCO2 as the efficiency is limited by the primary coolant temperature. So there will be more risks than benefits in combination of this, let's say, generation 3 reactors with sCO2. And as I said before, first application, we need to verify the cycle. That's all from my side.
Thank you very much, Otakar, for your presentation. It was great to listen to it. I suggest to the audience to keep asking our questions. I see that there is already one for Albannie. I'm sure that she will address it. So if you have now questions for Otakar, please feel free to ask him as well, and he will definitely answer. Who is next? So the next speaker is Paul Levisse, who is a rotating equipment manager at NAAREA, which is a French startup developing molten salt nuclear reactors and sCO2 conventional islands. He leads NAAREA's development on sCO2 cycles and integration. He's a graduate of École Polytechnique in mechanical engineering and material sciences. So I see that Paul is already sharing his screen, so that's great. So Paul, over to you. You are still muted.
Should be better now, sorry.
Yes, it's better.
Okay, thank you so much for the floor. I'll start off with a quick presentation of what NAAREA is, because most people may not know it, and to understand better what is a small modular reactor applied to CO2. So NAAREA is wants to provide energy, so we're a utility developing nuclear microreactors, so using nuclear spent fuel, plutonium essentially, on an 80 megawatts thermal and 40 megawatts electrical scale. And so we're building small modular reactors in factory, so 4th generation, molten salts and fast spectrum. So lots of words in there. So it's nuclear reactors. 4th generation means it's the advanced reactors of which Albannie and Otakar have already spoken. Molten salts is our fluid transfer medium, so it's like molten salt, like your table salt, which you put up to 450 degrees Celsius, and then it melts, and that's our coolant fluid. And fast spectrum means we're burning spent nuclear fuel, which is always good. So we're a utility, so we sell electricity, and that's the origin of the word NAAREA. So I'll go quickly over this because I think we want to apply it more to sCO2, but it helps to understand that we're trying to sell electricity using small modular reactors, and our key target and our key market goal is mostly industrial plants. That's our primary target, because in this 80 megawatts thermal, 40 megawatts electrical range, you're really in the range of what a big industrial plant will ask for in terms of electricity needs. And so with small modular reactors, you can place yourself extremely close to your client, and so you can supply them with either heat or electricity depending on their needs. And so that's more or less what we're aiming to do at NAAREA. So use a molten salt reactor, which has passive safety because the salt expands and stops its nuclear reaction. We use spent nuclear fuel, and we build all this inside a 40-feet container in a factory that we can then ship or transport to the client. And so that has a lot of advantages. So we're building small modular reactors with molten salts. We want to develop them in series. So we've got the objective of making a serial industrial approach. And that's really the advantage of SMRs, which is you can build them in factory. So use standard industrial methods to reduce the costs and increase reliability, and then deploy them on site and have since it's very small and we can put it into a container, we can have limited civil works. So that simplifies installation and commissioning. And the last point is, since we're a utility, we sell electricity as a service. We're not selling nuclear reactors. We keep we keep the responsibility, and we sell electricity or heat as a business model. So that's a very, very fast draft through what NAAREA does. Small modular reactors, molten salts. The question now is why would we, and we sell electricity and heat. The question now is, why do we want to do sCO2 with that? And that's my next slide. So when we look into it a bit more in depth, what we have is can I get a small, no, I can't, sorry. What we have is we have a reactor island, which is 80 megawatts thermal, and which outputs molten salt at 650 degrees Celsius. So that's molten chloride salts. And then we have to transfer that somehow into electricity or heat. Our target is to use sCO2 for that, for several reasons, which I'll explain. Everything that comes out of this reactor island is standard molten salt. It's conventional. It's not radioactive. It's non-contaminated, because every aspect of handling radioactivity is undertaken within the reactor island. So everything that is radioactive is inside the reactor island. All we get out is heat in the form of molten salt. So our target there is to use a recompression Brighton sCO2 cycle, which is fairly standard, and Otakar has spoken about it at length, and couple that directly to the grid and supply potentially electricity or heat depending on what the client wants. We want to also be able to do load variations to follow the client requirements. So that's also what we're aiming to do with the sCO2 cycles. And it's a standard industrial application here, because all the nuclear safety requirements are handled by the reactor island. Last element, which is important since we want to be as close as possible to the industrial plants and sites, is we're trying to go for air cooling as the ultimate cold source for the cycle. So have a water loop and then cold air to, just ambient air to cool the cycle, because then we can have more resiliency compared to the industrial site locations. So why would we want to do sCO2 with molten salt SMRs? Because we could do just standard steam-powered cycles. But there's, at least I've identified 4 of the most significant characteristics of molten salt small modular reactors, which make it a good match with the sCO2 cycle. The first being temperature. Molten salt is a high temperature fluid because it melts at roughly 400 degrees. So you have to use it above 400 degrees. and it can go up to 700, even potentially higher, but then you get limited by more materials. But we've got that operating range between 400 and 700, and well, as Otakar mentioned, sCO2 really starts to have a significant benefit compared to steam above 700, or at least above 550 degrees Celsius. And we could go for supercritical water, but supercritical steam has such a high cost in terms of thicknesses that it makes more sense on larger plants rather than plants of this size. And there's also a good match between the temperatures of the molten salt and the CO2 temperatures across the main heater. That's more for the thermodynamics of the cycle, but 400 and 700 is really a good match for sCO2. Second aspect, which interests us a lot, is capacity. These molten salts, they enable for very compact reactors, especially when you couple them with plutonium. You can get something where the core of our reactor, which does 80 megawatts, is roughly the size of a dishwasher. So then you've got auxiliaries, etc., around it, but it's really, really small. So that's what enables you to do a container for the reactor island. If we've got such a compact reactor island, it's a bit of a shame to waste all that capacity by adding a very large conventional island, whereas sCO2 enables for compact turbo machinery. So we could have a compact reactor and also compact conventional island. So get a small footprint of the plant for installation on industrial sites, especially as these industrial sites, they're often space constrained because, well, other industries have been built around it, or they just have a parking lot which they can provide. So we have to be able to fit on a tight spaces. So capacity is really important there. Third aspect of molten salt SMRs is reactivity. If you're in a fast neutron molten salt reactors, you can react, I won't say instantaneously, but almost, to load changes because you've got low thermal inertia. You don't have something called xenon poisoning, which you have in conventional thermal reactors. So these reactors, they can react to load changes very fast. If you're on a large steam cycle with large thicknesses, you don't get that reactivity, whereas the CO2 transient response is seen as faster than steam. It still has to be demonstrated, at least in situ in real plants, but we expect a benefit there. So we could go for more load following of the client. And the last point is, well, the installation. So as mentioned, we want to be these molten salt reactors, we want them as close as possible to the end users, sometimes in remote areas. And the sCO2 cycle enables us to do dry cooling, so we can use directly ambient air, and we don't have to add makeup water as we would in a standard steam cycle, so that reduces the installation constraints and increases resiliency. So we see that as fairly positive. So these are four of the key points that make sCO2 match really well with molten salt, and which is why we're pursuing this. When we talk about sCO2 development, because that's the title, R&D activities for in Europe for sCO2, what is NAAREA undertaking? So we've got questions for more a fundamental point of view on salt and sCO2 interaction. What happens in that main heater if there were to be a leak, for instance, of sCO2 leaking into salt? So on that, we're running calculations. We're going to start doing tests of what really happens when you mix sCO2 with these chloride salts. We're launching sCO2 material corrosion tests because, well, that's one of the questions. The mechanics of the mechanisms of corrosion and sCO2 are still, well, in the process of being understood. Lots of work on sCO2 steady and transient modeling. I won't go really too much in depth there, but there's really questions on we're a private commercial company, so we want to commercialize these. The question is, what is the techno-economic optimum for the cycle design? So where should we set our turbine inlet temperature versus material costs? What do we want to use for our compressor inlet temperature? How do we optimize the recuperators for pinch and cost? And all the questions for all that will come as in terms of transient and accidental conditions. So what happens when you shut down the reactor? What happens when the turbine trips? All these questions of coupling sCO2 with a nuclear reactor in terms of, coupled control. Overall integration, so NAAREA is positioned as EPC and operator. So that means that we're really integrating these equipments and the sCO2 cycle. So we're turning to specific manufacturers and dedicated suppliers for everything that's turbo machinery, heat exchanger, and all the other equipment. So we're more of an integrator, and as such, our main challenges at this stage, they lie more in the question of the demonstration of techno-economic competitivity. So these cycles are really new, so we've got a bit of difficulty projecting the CapEx and OpEx for series production, but that's a critical element if we want to make these cycles viable, is being able to project into, well, a commercial benefit in the end when we put these into series production. We expect the efficiency benefit and the capacity will really be worth it, but we have to get to these series numbers. And there's also more a development challenge, which is there's no off-the-shelf solutions for turbo machinery and heat exchangers, which are the two biggest components. So we are launching into specific feed studies and supply chain development, but it's a combination of both component development and cycle development and integration development, which makes it challenging. And as a last small challenge, and as a conclusion, one small challenge which is specific to molten salt reactors is that salt as CO2 heat exchanger, which you could also see in concentrated solar plants. But this one is at the crossroads of multiple challenges. So we're talking about the heater, which is in contact between the SCO2 cycle and the nuclear island. It sees, on one hand, SCO2 at 250 bars and 630 degrees Celsius, so very hot and very high pressure, and molten salt at 650 on the other side. There's a lot of questions there. We need to find something that resists the corrosion by the molten salts, which corrode almost all alloys, which is also highly dependent on salt purity. And we have to handle the other corrosion mechanisms on the other side of the heat exchanger, which are linked to the SCO2 in itself, so carburization and the high temperature mechanisms on SCO2. It's both high pressure and high temperature. We want it to be compact and still not too costly, so lots of different challenges. And one specific challenge to using salt, which is it has to be drainable. We want to be able to drain the salt and not have salt solidify within it. So lots of challenges, but that I hope has shown you why we're interested in sCO2 at NAAREA and the interest for small modular reactors in sCO2.
Thank you very much, Paul, for your enthusiastic presentation. Well, before we go to the last presentation, I want to thank to all the participants for asking questions. So there are actually questions for all the speakers that's spoken so far. So Albannie, Otakar, and Paul. So dear colleagues, don't hesitate to answer them either on writing or orally if this is too difficult to write or if it's too lengthy. Well, anyway, so the last but definitely not least speaker of today is Jack Akers. He is the STEP Power and Cooling Lead for the UK's Atomic Energy Authority. Working within the STEP project team, Jack's focus has been on developing power generation elements for fusion. Jack joined the authority in 2020 following a career in oil and gas and specialty chemicals. So Jack, you have the stage.
Thank you very much. Yes, so I'm Jack Akers. I'll give you a very brief overview of fusion energy and the role of CO2. So, I mean, the main aims here is to give you a bit of a flavour of what fusion energy is, give you a bit of an insight into the project I work on, which is STEP, and that's very different to potentially the STEP demo project that you guys are used to hearing of, and then really want to go into what role CO2 might have to play in actually establishing fusion energy on the grid. So first thing, what is fusion? So fusion is a process that powers some stars by fusing hydrogen at the core. So it's quite different to fission in the sense that it's relying on atoms colliding rather than splitting, but obviously both processes rely on the mass deficit of subatomic particles to actually generate energy and heat. So why should we do fusion? So obviously on the left here I've got a very typical graph called global electricity mix, which sort of shows obviously that by 2050 we're still going to be reliant on fossil fuel, however large increase in renewable energy. So the role of fusion is not to displace this renewable energy, but rather supplement it with base load power to effectively be part of the mix, be a new source of energy that can supplement our electrical mix and ideally decarbonize our grids. We also have on the right a number of processes that rely on high temperatures, which is actually a common theme with some of the previous presentations. So indeed, we're not looking to just decarbonize the grid, but also looking to decarbonize our industries. And you can sort of see how fusion heat can go up to actually quite high temperatures, potentially in future commercial variants, and that is quite nice to adapt to certain process applications. So generally speaking, there is obviously a global demand for reliable, dispatchable and safe clean energy, allowing us to reach net zero. And where it's quite different to fission is on that safety element. So there's obviously no risk of runaways in a fusion machine, and also I think there was in the cloud something about difficult regulations, and the UK in particular, fusion will not be regulated by the typical fission regulators, which is obviously an interesting opportunity. So that's what it is and why, but how do we do it on Earth? So obviously fusion in the sun occurs at immense pressures and immense temperatures, and to replicate these conditions here on Earth is very difficult. So it requires obviously very high vacuum to minimize any contaminants. It requires very high temperatures. In fact, we need higher temperatures than the sun to actually overcompensate for the lack of pressures. So that's up to 100 to 150 million degrees, whilst the sun is typically 10 million degrees. And we also need fuel. So typically the most fuel that gives us the best bang for a buck, so the most energy for a given temperature is deuterium, tritium. Deuterium is widely available naturally, but tritium actually isn't available, is man-made, and has to be bred locally using lithium and lithium and neutrons. So that's great. That's how we generate a fusing plasma at 150 million degrees. But how do we actually confine this plasma in place? Well, there are a number of techniques. One is magnetic, another is inertial confinement. I will talk largely about the magnetic confinement technique, which looks at using a tokamak. So that's a magnetic combined fusion device where a plasma current is induced using a central solenoid transformer, which allows for the confinement of that plasma within the confines of this toroidal magnetic field in blue. And then we also have colloidal magnetic coils, which help us shape and control the placement of the plasma itself. So obviously that's why it's called magnetically confined fusion. So that's a brief overview of fusion, but who is doing it? So there are a large number of devices globally in the world at the moment. JET and MassDew are machines which exist at the column where I work. So JET has just recently been closed. MassDew is still going. JT60SA and other supporting tokamaks such as West or DTT also exist, and JT60SA is in Japan, DTT is in Italy, and there are a few in France as well. But these tokamaks here are actually supporting ITER, which is the largest plasma experiment ever to be built. Is a massive infrastructure undertaking in the south of France, but will remain a experiment rather than a power plant. These will pave way to a number of power plant projects. So STEP is the one I work on, spherical tokamak for energy production, which is based on a spherical tokamak. So you'll see it has a slightly different shape to conventional tokamak like ITER or Demo. And Demo is based on ITER. The main thing to bear in mind is that while these ones on the left are experimental devices, these ones will be power plants aiming to put net power onto the grid using these various tokamak devices. Another approach is the US approach. So they announced a bold decadal vision, which rather than build their own sort of significant infrastructure projects, they're looking to fund a number of promising startups. So likes of Commonwealth Fusion or Tokamak Energy, which are spherical tokamak based. The other ones that are stellarated based, which is a very similar technology to the tokamak, still magnetically confined, but there are also others which they are funding, which are sort of more based on lasers or inertial confinement. So what is STEP? Spherical Tokamak for Energy Production. Like I said, is the project I work on. This is the mission. So it's to deliver a prototype fusion energy plant targeting 2040 and a path to commercial viability of fusion. So a few interesting things to pick out here. Obviously, the constant joke is that fusion's 30 years away. We are committing to achieve it in the next two decades. And we have also committing to a commercial viability of fusion, so a path to commercial viability. So a prototype won't necessarily be commercially viable. However, the subsequent power plants that are based on the STEP prototype will have to be commercially viable, and we are establishing a whole program to ensure that. So that's the mission. What is it? Like I said, spherical tokamak for energy production, fusion power plant, which will demonstrate four key things really. This net energy piece, so it will actually put net power onto the grid. Fuel self-sufficiency, so you'll remember I talked about tritium. It will demonstrate the ability to breed enough tritium such that it can run itself. It will be maintainable. So this is very tricky on fusion power plants, and a very critical aspect in ensuring that we are able to demonstrate commercial power plants. And obviously, I have this piece on the commercial viability. It will be delivered in 3 phases. So the first one is to develop this concept design and select a site. We have actually selected a site in the UK, in West Burton, and we are just finalising our concept design now. We will very soon be entering a detailed engineering design phase, with sort of aiming to get to a 3rd phase of manufacturing construction in the 30s, intending for operations starting around the 2040s. It is a spherical tokamak basis. It has a slightly different shape to what I showed earlier in the tokamak picture, the conventional tokamak. It has a much skinnier center column, a much higher, lower aspect ratio, and it has a number of other facets to it, such as novel exhaust options. By being sort of skinnier and taller, there are fewer small magnets. It will require smaller buildings, and therefore will be lower cost due to its compact nature. Which sounds familiar. So now to talk about the power plants, or the power cycle aspect of STEP. So one thing to bear in mind for any magnetic confinement source is that there is we start off with fusion power from plasma. This then imparts neutronic heating to the tokamak. This will generate heat, turn it into mechanical work in a turbine, which will then, in a generator, give us power that we can either put on the grid or recirculate. So we actually have to do both. When we generate power, we'll put some on the grid, but this recirculating power is a fairly unique aspect of fusion in the sense that it's so high. And this is because we need a number of very large-scale fusion-enabling systems, such as our heat and current drive, which heats our plasma to such high temperatures. This is very power-hungry, especially at low scale, but we have other parasitic loads, such as our magnets. And so because of this interesting power balance, we have different ways of defining our efficiencies across the plant and energy gains. So things like Q are referred to quite often. This is a ratio of our fusion power to auxiliary power. Obviously, P net is quite obvious as the net power generate, which is the power we generate minus the recirculating power. And then a much wider efficiency for the plant is this QN, which looks at the net power divided by the fusion power we begin with. So obviously, efficiency is key, and I've listed 4 key challenges. One of them is efficiency. The other one is heat integration. The third one is this need for flexibility. And finally, we still need to demonstrate viability as well in the long term. So I'll go through each of these one by one. But the need for efficiency, like I said in the earlier diagram, there's a lot of high power flows going through, and this is a power balance of our prototype. It looks like significant heat being developed from the tokamak. Quite a lot of power generated by our power cycle, but as you can see, most of this power is then recirculated back into our fusion enabling systems, such as our heat and current drive, and so only a small portion is left to go onto our grid. As we go to a commercial machine, these parasitic glows do not scale linearly, so they should cap off, and effectively any additional power we can generate here should be all power we can put to the grid. Obviously not quite as simple as that, but broadly speaking. So how does CO2 come into play here? Well, obviously we are seeking high efficiencies across the board, which includes our thermodynamic cycle. The more power we can convert into electrical power from our fusion power, the better off we'll be in terms of the amount we can put onto the grid. And that is why CO2 cycle is quite interesting, because at fusion relevant in sort of turbine inlet temperatures, the CO2 cycle does seem to be very, very promising in terms of performance. Now let's talk about heat integration. So the tokamak is not just one machine. Unfortunately, it's made of many different components, which all have very special heating or cooling requirements, I should say. So for example, our blanket is where all of our tritium breeding happens, and there's a volumetric heat load, which therefore means we can get quite a high temperature out of it, whilst our diverter we'll see is effectively what we call the ashtray or the tokamak, and we'll see very intense heat loads as the plasma comes through here, and that will see very, very large surface heat loads, which must be cooled at relatively low temperatures. So we can't get good grade heat out of this. So this presents a bit of an issue in terms of heat integration, trying to integrate all of these different types of heats from these different components into a single cycle is challenging, especially with incumbent technology. So what's quite nice about the recompressed Brayton cycle in particular is that you can start manipulating the enthalpy gap within that cycle to integrate these different grades of heat. So for example, by adding the low temperature grade heat as a bypass to your recompressor. So the final challenge I was going to talk about was this need for flexibility. So tokamaks are inherently pulsed, and this is a view of the EO demo pulse operational time frame. So they're looking at doing a 12 or 10 minutes and then actually being operational for 2 hours. Step might not necessarily have these constraints, but it just goes to show that there is this on-off piece where there is a need for flexibility on the power cycle as well. There's also, just more generally speaking, rapid operational dynamics. So our startup and shutdown will be fast. Here it's shown as here it's shown as 10 seconds. 100 seconds even. So having a thermodynamic cycle that can help us minimize the gap between when we have established fusion power and actually are generating power to then be able to supply all our parasitic loads that are internal is quite important. Finally is the fact that we will be a prototype. So it will be a prototype power plant, which means it will often undergo trips or unexpected events or pulses that are run short because something's gone wrong or something's gone wrong during the ramp up. So again, a power cycle that is forgiving is helpful. So where CO2 come in, this is the result of a piece of work we did using the step demo dynamic model, which obviously needs a lot of demonstration, but goes to show that there is something in trying to use CO2 to help us ramp up and down the turbine and other turbine machinery quite rapidly, which lends itself well to our demands. So just as a very quick conclusion, where can CO2 help us? What can help us with all these things? So need for efficiency, obviously we've got a high efficiency with our CO2 solution. Need for heat integration, we've shown that the RCBC lends itself well to that. It's highly responsible, which addresses our need for flexibility, and then this needs to be viable. I didn't really talk about it, but it is obviously compact and comparative, as shown by the classic Dostal diagram here, which it lends itself well to the general message we are trying to portray in terms of a compact power plant. And that was it. Thank you very much.
No, thank you very much, Jack, for your presentation. I'm sure that everyone enjoys listening to it. And well, this is it. You have heard all the 3 presentations that we have programmed for today. So I will give the floor again back to Albannie. and obviously all the speakers, because they are available for answering your questions. I see in the Q&A section that there's quite a few questions which hasn't been answered yet. I'm sure that Albannie will cover this and she will take care of it, right?
Yes, I was just looking for the question with that reply, if I can have some reply. But lots of questions were okay. There was some question for Paul, mainly on some dates or target for NAAREA. So I think that Paul will be able to reply. Okay.
Yes.
I don't know.
Should I answer now, Albannie?
Sorry. Yes, if you
Yeah, sure, I can answer.
if you want to give us some replies, it's okay for us.
Yeah, no problem. So NAAREA's target is for commercial, beginning of commercial, first of a kind by 2030. As mentioned, it's a regulatory environment, so we also have to work with the regulator, but that's at least the commercial target and what we're working on.
So yes, we already also have a question for Otakar. Could you please comment on the current understanding activation product of carbon dioxide due to irradiation from the fast reaction when using carbon dioxide cycle as direct cycle? Very complicated question.
Very hard to answer.
Yeah.
Okay, I am not a specialist on that topic, but I was a part of GFR development focused project in the past, so it was cooled concept cooled by the helium, but I think I can partly respond even the second question about the nuclear waste which creates. It's again not my topic. Once you use gas-cooled fast reactor cooled by CO2 or helium or whatever gas, so it can lead us to closed fuel cycle, which is fine. When we can use the spent fuel again and try to burn some products which are burnable in fast spectra. I remember that there were some issues with americium or other products which can be partly burned in gas fast spectrum, but it produces also some new isotopes of americium. So that's it. I think it's not affected by CO2 or other gas itself. It's more about reactor physics. And I'm sorry, I'm not a reactor physicist, but generally I can say that it has some advantages. We can use some spent fuel again. But of course, there are some products which are also created in a fast reactor. And generally, about some activated products, it's again I was involved in some projects with helium, and we operate some helium loops. So I have some basic background on that, but very basic. It's not about activation of the gas itself. Maybe in using of CO2, it can the CO2 doesn't need to be so stable, so it can be affected with the neutrons and even with so high temperatures like 650 or even higher. So the CO2 can partly decompose. Then you will have there some oxygen and carbon and some more corrosion products can occur, and it's mainly the question of the construction material which are used in the reactor, as they can create some corrosion products which can flow through the core and they can be activated. So then it's again not so much about the cooling media or working media, but it's more about some corrosion products which can be activated. And regarding, there is a question regarding storage of that waste. So I'm not going to talk about storage of nuclear spent fuel, as this is not really a question to me, but some impurities in the coolant which can be activated, I think it can be simply catched by some mechanical filtration and stored. Using of some technologies, as there are more of them.
Yes, the question of use of supercritical CO2 as direct in a direct cycle, it's always something that we have a lot of studies on, for example, for neutronics analysis, in order to understand what is the behavior if there is some incident, if there is some accident, or for all the possible transients, and also to be able to mitigate, to find the best solution for safety. It could be passive safety, active system. So it's always a question that even for the current plant, we are still always doing research on this topic in order to increase even the safety of the current and the future plants. So it's difficult to say that today we have all the answer, but it's easy to say that we are working in order to have the most answer possible, and so the most solution possible for this type of question. So there is also some question from NAAREA, especially about the heat exchanger. Okay, so I will maybe let Paul reply if it's okay. We have some question also for Jack with a primary feed that you plan to use in the fusion plant.
Yeah, so I did respond to that. I just give a brief overview. So we're looking at a mixture of helium and water for the primary coolants. The reason why it's different coolants is because our in-vessel components, if you remember the slide I had, showed that we had different in-vessel components, and because of the sort of particularities of each of them, we need to cool them with different coolants. So the helium can go up to 600 degrees, whilst the water will go up to 250, which then means we have this demand for heat integration, as we have different types of heat sources. I think Damien was comparing to West, which is at a much lower temperature, and the reason why that is because that is not generating power, and therefore there is less of a demand to drive those temperatures higher, especially as well as they will run for lower periods of time in the pulses. So there is a temptation to have sort of batch processes on the cooling system, but also to sort of cool them at much lower temperatures to basically benefit from material and durability from doing that effectively on your component. Hopefully that makes sense.
Okay. I think that I saw a raised hand, but maybe it was not okay. There is a question, but it's also a question from me as a moderator. On a personal point of view, I think that the heat exchanger will be one of the key components for the deployment of this type of cycle using supercritical CO2. So the question to all of you is, how do you consider the current development of heat exchanger for your design? I think that some of you are maybe on internal developments. Some of you maybe will think about commercial use of commercial heat exchanger. So the question is, okay, how do you face to this current question about the inspection with this type of heat exchanger and the qualification of this component for the future? Are you confident with a very to be that we will be able to have soon some qualification or certification for this type of compact heat exchanger? Or also, how do you consider your supply chain for this type of component? It's quite the complicated question. I'm sorry. So I don't know, maybe Paul, because NAAREA.
Yeah, sure.
Yes,
we've got the shorter timeline.
Sorry.
So as you mentioned, yeah, the primary heat exchanger is one of the most critical components, at least seen from the conventional island. When you look at the nuclear heat exchangers, they're even one stage higher in terms of complexity. So we've got two options there, which is either we go for the highly compact directly, and we have to go through qualification. And what we've got an advantage, which is it's not nuclear qualified in our case, since it's on the conventional island side. It's got almost no nuclear safety elements attached to it, but we do have the industrial qualification. Question there is, okay, can we get a solution with the correct materials that's industrially manufacturable by 2030? It's a challenging element. We have the alternative, which is the backup as a pre-series or in the first stage of production, which would be, okay, we go for a less compact, advanced shell and tube heat exchanger as a backup, which will be less compact, but at least we'll be able to have something in lieu of the actual very compact high temperature heat exchanger. It's not the greatest solution because it does put some constraints, but that's at least our path forward, which is we want to qualify these printed circuit heat exchangers highly compact with materials that resist both to molten salts and CO2. Challenging, and we've got some very challenging aspects in terms of manufacturability and demonstrating that these are qualified from an ASME point of view or the European equivalent, and then we'll go for a backup in which if that solution should fail. So that's more or less how we see it. There's still some road to go.
I can give a very quick overview from my side, Albannie, if that's helpful.
Yes.
So I mean, so like I said, we're considering a recompressed Brayton cycle. We also have heat exchange between helium and CO2, which needs to happen. So we're looking at probably 4-ish gigawatts of heat exchange happening, which is very significant, and we need all of that delivered by 2040. And obviously the as our concern is both trying to show commercial viability, which is partially through being compact, but also in terms of maximizing our efficiencies, and using traditional heat exchanger technology can be limiting in that sense. By the time you've manifolded it all in, PCHE or high performance heat exchangers are very attractive for this application. So it is primarily a supply chain concern, although we do want to understand more about its performance during transient periods. And obviously there is still this question of how we maintain and inspect those particular heat exchangers. In terms of the sort of standards and regulations behind it, we're in a sort of similar position as Paul, that we will not be regulated by the ONR in the UK. So we have a little bit more freedom there, and are a little less concerned about trying to demonstrate it in that sense.
Okay, thank you, Jack. This question bring me just a current question. I, on a personal point of view, think that for this component, we can develop them for the nuclear or for some other energy, so with collaboration with people from other energy. But do you consider that, for example, for the turbine, for the heat exchanger, we will need to have different developments? So, for example, development for supercritical CO2 turbine for the nuclear plant or for the gas plant, and if it's no, so if we can have a mutual development, it brings me a question: what can we do in order to accelerate the deployment of the technology, of the development of all these components?
I'm not sure I have the answer to your second question, Albannie. For the first one, at least, personally, I think that what we're developing on the sCO2 side could be applied to, it's agnostic to the heat source. So, okay, we're developing it for a nuclear reactor. It's a bit tailored to our thermodynamic spec points, which are dependent on the nuclear reactor. But if we were to have some different source of heat with perhaps similar conditions, okay, we could use the conventional island. I won't say as is, but there's no reason for us to develop something different just because it's nuclear or non-nuclear on the other end. What really matters is what's the thermodynamic spec points we're seeing. So I'd say there's room for collaboration and to try and find some synergies between the different industries that could use this technology. The how, I don't know the answer to that, but.
Yeah, I would say potentially one of the changes between more conventional applications of the CO2 cycle might be the dynamics that we have. Obviously, you'd have to investigate that a bit more. I think that's particularly true in my case. And then the other potential difference might be the temperatures of the sort of inlet turbine temperatures. I think, Paul, you were showing sort of up to 650 of your molten salt, but obviously in a CSP they're looking at a bit higher. Naturally, it should be easier to develop a turbine at a lower temperature, but it still has to be potentially developed if you're looking at sort of cheaper materials to use in there to maximize the low temperature benefit. So that might be a difference I can foresee.
Okay, I don't know. We have just few minutes. I don't know if there is some question in the audience.
Well, I want to remind you that everyone has a microphone enabled or a camera as well.
Yes.
So you can just start talking if you want to. If you unmute yourself, we will hear you.
So no question. Okay.
First of all, thanks a lot. It was highly interesting.
Okay, yes, because my question was the last, and I think that okay, just for conclusion, as we said and as we show it in the other episode and in this current episode, there is a very good dynamic on supercritical CO2 cycle, and we need to find a way to pursue this dynamic and to be together in order to go closer to the market with this technology. I really hope that for the nuclear design we saw today, that we will be able to see real plant deployed really, because it could be very interesting, and they will bring us a lot of new usage, for example, for the nuclear, as Paul, Otakar, and Jack explained. It's not only for electricity, but it's also for some other use. And if we want to face to the global transition and to be able to decarbonize, for example, industry, we need to be able to use this type of heat, I think. Okay. The question is, yes, one of my conclusions will be, okay, I hope that we will be able to pursue all this development. On the nuclear part, we know that we will need to face and to deal with the regulation and the qualification of the equipment. But I'm really optimistic that if we are able to work together with all the other energy, we will be able to find some solution about some question about, for example, these materials that we need to use, about the in-service inspection, which is a very important question for the nuclear plants, especially for the heat exchanger in-service inspection. And I hope that today you learned some new information about the fact that we try to be innovative in the nuclear, and we are not closed to the other works of the people, because we cannot have this readiness level now if the former works, for example, during the European project, in the former demonstration outside Europe and inside Europe, didn't happen and didn't occur, okay? Because if we are confident to have this turbine with a supercritical CO2 cycle, it's really thanks to the job done by the turbine companies in order to develop this type of element. The same for the heat exchanger, and the same for all the components which we deal with the supercritical CO2. And for the current, and for example, the direct cycle with carbon dioxide, we know that there is a lot of research in nuclear, okay, but all the research on the materials, on the behavior of carbon dioxide is also shared with all the other energies. So my last word would be, okay, we need to continue to work together and to make some studies, some research on the carbon dioxide cycle, because it will be a benefit for all the energy and for all the society. And that's my last word. On time.
Thank you, Albannie. Are there any other questions? Any other parting messages from anyone?
Happy to participate in these tests and research projects, and we are already involved in a couple of them. So from Kelvin on site, yeah. Yeah, thank you for your kind words. We are happy that you liked it. Well, if nobody has any other question, then let me thank everyone, the speakers in particular, for making time in their busy agenda, to Albannie, of course, for greatly moderating the session, to all of you, the participants, for coming and for engaging with us, for your questions and the Slido, etc. And obviously also to my colleagues from the sCO2 working group from ETN, because without them this would not be possible. We have been very many today. We have been almost about 100 people
which is a very encouraging number, and it does motivate us to continue in this webinar series, and we will. So you will be obviously informed, as you always are, about the next session. In the meantime, obviously, I will share the video and the presentations. If after the webinar you still have questions, you can contact us and we will answer your question, and we will again get back to you. So thank you very much. Have a nice rest of the day, and till the next time. Goodbye.
Thank you. Bye.
Thank you.